Hello, pre-calculus students. Today we are going to continue our notes in lesson 5.1.1. We're going to be looking at the backside, and the backside focuses on simplifying these crazy-looking trig expressions using the identities on the front. Now, before we get started, I will say I have probably about 4 examples planned. I'm not going to take the time to go through all these examples, but try and show you several. And I'm going to try and give you tips and tricks along the way. I would encourage you to be flipping back and forth and checking out those lists of identities to get ideas. But what you have up here, I wouldn't say they're 5 steps, but they are 5 things to consider, or kind of 5 pieces to check when you're trying to look for ideas of how to simplify these trig expressions. One item is, the first thing listed is create common denominators to combine fractions. So that is sometimes necessary. 2 is just the opposite. Sometimes you separate the numerators by dividing each piece by the denominator. 3, we're going to be doing some factoring and foiling. Things like factoring a GCF out or foiling. 4, look for Pythagorean identities. I always say look for when there are trig functions with squareds and or a plus or a minus 1, or trig functions squared and added or subtracted together. Those are often Pythagorean identities we want to look for. That'll be a big thing. And then 5, sometimes we just need to take the entire problem and change it all to sine and cosine and work with sines and cosines. So that's sometimes an idea. So let's look at example 1. Our goal is to simplify this. As I look ahead to the answer, it comes out to be a single trig function once we do the simplifying. So it reads sine cubed x plus sine x cosine squared x. And with that in mind, obviously 1 and 2 aren't really necessary because there's no fractions to worry about. 5 isn't really anything to worry about because it says change everything to sine and cosine. Well, it is already all sine and cosine. So that takes us to options 3 and 4 up above. Factor or FOIL and look for Pythagorean identities. As you start thinking about factoring, is there anything you see you can factor here? And if you look at one term being sine cubed x, the other term being sine x cosine squared x, notice both terms have a sine in common. And so our first step is going to be to factor a GCF. I'm going to try and write, probably looks like in red, what the steps are we're doing. So as we factor a GCF, sine cubed and sine, there's one sine x in common. So I'm going to put sine x out front. If we have sine cubed x and you divide by sine x, same idea if you have x cubed and you divide by x. What remains? And that is a sine squared x. Carry down the plus sign. If you have sine x cosine squared x, you divide away the sine x, we are left with cosine squared x. And so first step was to factor a GCF out. Now as you start looking at this, we have sine x times sine squared x plus cosine squared x. And if you've become familiar at all with those identities on the front side of the notes, something should be looking familiar here. So please, by all means, flip back to those notes to see what looks familiar. What do we have in our parentheses there? Sine squared x plus cosine squared x? Is that a Pythagorean identity? It is a Pythagorean identity. So sine squared x plus cosine squared x is equal to 1. That means sine squared x plus cosine squared x can be replaced with 1. And that's because it is a Pythagorean identity. So if I take the sine squared x plus cosine squared x, it's in parentheses, I replace it with 1, carry down my sine x out front, and my expression now becomes sine x times 1. And sine x times 1 is sine x. So there's your first basic example of simplifying a trigonometric expression. Oops. Sorry, I'm trying to adjust this a little bit. There we go. Okay, so in that we looked at factoring and foiling, or factoring basically, and we looked for Pythagorean identities. Hopefully you've seen a little bit of an example of how that works. Let's look at B now. Secant x plus 1 times secant x minus 1 over sine squared x. Go back and look up at those 5 options up front or up top. Combine the fractions, separate the fractions, factor or FOIL, look for Pythagorean identities, change everything to sine and cosine. And look at your numerator here. Secant x plus 1 times secant x minus 1. 2 parentheses. What can I do with those 2 parentheses if it's a binomial times a binomial? And I am hoping you're thinking FOIL. So we're going to FOIL here. FOIL the numerator, that is. Secant x times secant x. Now, as we talk about secant x times secant x, that's going to be secant squared x. I tend to write it like such, as secant squared x. However, it could also be written as secant x with parentheses around it. With parentheses around secant x with the squared outside. Okay, secant x times secant x is secant squared x. Secant x times minus 1 is going to be minus secant x. However, 1 times secant x is going to be plus secant x. Notice those outside and inside terms will cancel. And then lastly, 1 times negative 1 is minus 1. So hopefully you realize those are conjugates, so the middle terms cancel, which makes it nice. So I now have secant squared x minus 1 over sine squared x. Okay, so we FOILed on top. I would suggest you continue looking at that top. Secant squared x minus 1. Think identities here. I see squared. I see a squared function plus or minus a 1. So squared functions add or subtracted or add or subtract with 1s can often possibly mean a Pythagorean identity. Do we have a Pythagorean identity that involves secant squared x and 1? And we do. And in fact, I'm going to write it up here. If you flip to the front side, your identity I'm talking about is the fact that 1 plus tangent squared theta is equal to secant squared theta. And that is just the Pythagorean identity copied from the front of the page. Now, we have secant squared x minus 1. Can I manipulate 1 plus tangent squared equals secant squared to be a secant squared minus 1? When I say manipulate, I'm talking about just using your basic algebra. So how do I move the positive 1 to the other side? We're going to subtract 1. If I subtract 1 on one side, I subtract 1 on the other side. So then I will be left with the fact that tangent squared theta is equal to secant squared theta minus 1. So wherever I see secant squared theta minus 1, I can replace it with tangent squared theta. So right here on top, I have secant squared x minus 1. I'm going to replace it with tangent squared x. Still going to be divided by sine squared x. Let me comment while I forget. X is a variable, theta is a variable. Don't think of it as any more than that. Whether you use x's, thetas, doesn't really matter. So right there, guys, I took what secant squared x minus 1 equals and replaced it with tangent squared. And I did that using a Pythagorean identity. So there is yet another use of a Pythagorean identity. Now I have tangent squared x divided by sine squared x. There's a couple different ways to think here. I would maybe suggest we try a new thing here. And again, we can't really separate or combine fractions. However, what about option 5? Change all trig functions to sine and cosine. They can all be changed. Now, actually, before I do that, let me write this tangent squared over sine squared x. It's going to be helpful to some of you if you see this as tangent squared x divided by sine squared x. I think that's a little more visual. What do we know about tangent squared? Let me ask this question. What do we know about tangent? According to our quotient identity, tangent is sine x over cosine x. Well, that means that according to our quotient identity, tangent squared x is equivalent to sine squared x over cosine squared x. So right there, I am using the quotient identity. So now I have sine squared x. Let me back that up a moment. I have sine squared x over cosine squared x divided. How do we divide fractions? Well, if we divide fractions, we want to multiply by the reciprocal. Sine squared x as a fraction is sine squared x over 1. What's the reciprocal of that? 1 over sine squared x. We are multiplying two fractions, folks. What ability do you have when you multiply two fractions? Cross cancel. Sine squared x can cross cancel with sine squared x. And when I multiply this, I am left with 1 over cosine squared x. Now, we have it down to one trig function, but preferable would be to get the trig function out of the denominator. What do you know about 1 over cosine x? Cosine is the reciprocal of secant. So 1 over cosine is equal to secant, which means 1 over cosine squared x is equal to secant squared x. And that can be thought of using our reciprocal identity. And at that point, we're down to secant squared x, folks. We're down to one trig function. We're down to the end. Okay, again, I'm trying to show you some ideas. I know this isn't going to be great because it's a video. However, Monday I plan to go over questions with you guys and look at some more examples, look at some of our homework examples, and help you to understand a little bit better. So keep chugging along with me. Try and see some of these ideas. It'll take a couple of times before they really start to sink in. Okay. Example C. We have cosine x over 1 minus sine x over cosine x. And I'm going to cut to the chase and tell you I see two fractions being subtracted. Two fractions being subtracted, I'm going to go for a common denominator. Common denominator here, guys. in order to get common denominator, trying to find a place to write it here, we have to combine our two denominators. Right now, our two denominators have nothing in common. So when we put together for a common denominator, our common denominator is going to be the first denominator of 1 minus sine x times the second denominator of cosine x. Now, what I will ask, in my first fraction currently has a denominator of 1 minus sine x. What is missing from that denominator? And I hope you are saying cosine x. If we multiply the denominator by cosine x, we have to multiply the numerator by cosine x. So for our first fraction, to get that common denominator of cosine x and 1 minus sine x, we're going to multiply top and bottom by cosine x. Let's go ahead and multiply that. What is cosine x times cosine x? That is cosine squared x. My fractions are being subtracted, so I'm going to go ahead and carry down the subtraction sign. And we're going to repeat the process with the second fraction. My second fraction has a denominator of cosine x. What part of the common denominator is it missing? And it's missing 1 minus sine x. So that means I'm going to multiply numerator and denominator by 1 minus sine x. Now, I'm not going to quite multiply this one. I'm going to wait till the next step. So I'm just going to copy down the fact that it's going to be sine x times 1 minus sine x. So that was getting a common denominator. Let's do some cleanup. On top, cosine squared x is still cosine squared x. I want to take that sine x and I want to distribute it. Now, keep in mind that sine x is a minus sine x. So minus sine x times 1 is minus sine x. Minus sine x times minus sine x is plus sine squared x. In the denominator, I'll be honest, it's hard to know sometimes. Do I multiply that together? Do I not? The numerator I usually need to multiply together. Denominator? It kind of depends. I'm not going to multiply it until I see need to multiply it. So right now, I'm going to leave it as 1 minus sine x times cosine x and see what happens. Now, look closely at that numerator and think about your identities. I've mentioned a couple of times. If you see squared functions being added or subtracted and or ones, do you see any squared functions being added or subtracted? I know there's an extra piece in the middle, but what do you see in the way of squared functions? There's a cosine squared x and a positive sine squared x. Does cosine squared x and sine squared x being added together mean anything to you? Maybe? Recognize it as a Pythagorean identity. So what I'm going to do is I'm going to rearrange my top. I'm going to keep the cosine squared x first. Then, those of you that haven't seen it yet, I'm going to just flip around. I'm going to move over the sine squared x and push the minus sine x to the end. The denominator, I'm still going to leave as 1 minus sine x times cosine x. Now, can you see the Pythagorean identity? I know on the other side it's written as sine squared x plus cosine squared x. We've got cosine squared x plus sine squared x. What can I replace cosine squared x plus sine squared x with? We can replace it with a 1, and that's because this is a Pythagorean identity. You'll notice I just wrote PI. I like to call them PIs because it's shorter to write. So, look at what happens. Cosine squared x plus sine squared x becomes 1. I still have minus sine x. all over my denominator of 1 minus sine x times cosine x. What do you notice? 1 minus sine x and 1 minus sine x can cancel because they are factors. 1 minus sine x is the entire numerator. 1 minus sine x in the denominator is a factor. They can cancel, leaving me with 1 over cosine x. What do we know about 1 over cosine x? Cosine is the reciprocal of secant x. So 1 over cosine x is equivalent to secant x. And that is a reciprocal identity. Okay. Get what you need there. I have one more I want to do real quick, and that is example E. So the middle one in the bottom. Trying to scoot this up without messing it up. There we go. Example E is our last example of the lesson for right now. Tangent of negative x times cosine of negative x times sine of negative x times secant of pi over 2 minus x. Okay, I mentioned something the other day when I was introducing these. I see negative x's in my parentheses. Those negative x's you see should make you think, oh, I need to use my even and odd functions when I see a negative x inside the parentheses. So we're going to use even and odd functions to replace those. And when I see pi over 2 minus x in my parentheses, that makes me think I want to use my cofunction identities. So let's try it. You're going to have to flip back and forth. Tangent of negative x, according to our even and odd identities, is equivalent to negative of tangent x. I'm going to put these in parentheses so things don't get confused. Cosine of negative x, according to our even odd identities, is positive cosine x. Sine of negative x, according to our even odd identities, is negative sine of x. And cosecant x. Oh, excuse me, I just gave away the answer. Secant of pi over 2 minus x, according to our cofunction identities, is equivalent to cosecant x. There we go. Now, at this point, we have 4 functions being multiplied together. Kind of a miscellaneous hodgepodge group there. We have not really done number 5 yet. Change all trig functions to sine and cosine. Actually, no, we did do that one other time, I think. But that's what we're going to do here, is we're going to change all trig functions. So I'm just going to say change all to sine / cosine, whatever that takes. So, tangent. Tangent, we can use a quotient identity, right? Tangent is sine x over cosine x, and since it was negative tangent, I'm going to say negative sine x over cosine x. Times, okay, cosine x, hey, good news, that's already sine and cosine. I'm just going to leave it as cosine x. I am going to make it a fraction and put it over 1 because my previous one was a fraction. Times negative sine x. Well, that's already sine cosine. I'm going to make it a fraction, put it over 1. So negative sine x over 1. And lastly, cosecant x. What do we know about cosecant in terms of sine and cosine? It is the reciprocal of sine x. So I can make that 1 over sine x. So when we change this all to sine and cosine, if you need a little more stuff to write down, We used quotient and we used reciprocal as the two ways. Oh my gosh, what was I doing here? Q-U-O-U-T. Oof, that was bad late, guys. Q-U-O. I don't even know how to fix that at this point. Q-U-O-T. Anyways. Okay, when we multiply fractions, let's do some canceling. Cosine x in the denominator can cancel with a cosine x in the numerator. A sine x in the denominator can cancel with a sine x in the numerator. A negative times a negative is a positive. What remains? Sine x. So all of that loveliness simplifies down to sine x. Okay, guys, I'm going to leave it at that. Try some of the homework examples for Monday. My plan as of right now is that Monday we will eat pie, and we'll look at some questions of these. I don't think I'm going to plan to check the odds until Tuesday, is probably going to be my plan. But I will tell you that the evens will be the next assignment as well. So right now, though, focus on the odds, use the back of the book to check some answers, and see what you can do with them, okay? Put some work into them, and we will reconvene Monday, and I will work to answer questions, okay? Bye.